This video is going to be an overview of the properties of quadratic functions when looking at the graphs. So a quadratic function is simply a curved shape. It looks like a U. The shape is called a parabola, and it can face upward or downward. So you have two different forms for the way the equation could be written for quadratics. Standard form is in the form of y equals ax squared plus bx plus c, and vertex form is in the form of f of x equals a times x minus h squared plus k. And then f of x or y, those are interchangeable since f of x is relating it as a function of x, and y is just simply a way to show the output based on x. What we want to make sure is happening in each form of these is that we are to the power of 2. This is how you would represent a quadratic. So here we're going to look for the vertex, which is the point where the parabola changes direction. This is the highest or lowest point on the graph of the function. The minimum or the maximum is going to be the minimum value of the function or the maximum value of the function. So this will be either the highest or lowest part of the graph, and it depends on if it opens up or down. So looking at our first example here, you can see that this parabola has the point here at the bottom. That would be the vertex. So the vertex for this one, I'm just going to say V, is going to be 2, -4. This is also, let me switch colors here. This is also the lowest point on the graph, so this is the minimum. That means that this graph will always have a value that is greater than or equal to that point. So we would say the minimum is y equals -4. It's just going to be the value of y because we're looking at the function. Now if we're looking at the second graph here, you can see that the vertex is located again at the bottom of the parabola. So this vertex is going to be located at 3, 1. Since the parabola is opening upward, this is also going to create a minimum value. So this one has a minimum where y is equal to 1. That means that all values of y here should be greater than or equal to that 1. Now if you wanted to pause for a moment and try the third one, then you can. For the third one, this vertex is now at the top of the graph. And so our vertex here is going to be located at the ordered pair -2, 1. And since our graph opens downward, this graph does not have a minimum. It has a maximum. So everything is below this value of the function. So this one has a maximum where y is equal to 1. Okay, for the axis of symmetry, this is going to be a vertical line that divides the parabola into two congruent halves. Since it's a vertical line, this will be a value of x as it runs through the x-axis. So it must run through the vertex. Here on this first graph, let's see if I can draw this in. The axis of symmetry would be through the vertex vertically here. That would put it at x equals 2. So that would be our axis of symmetry for this graph. On the second one, if we wanted to draw the axis of symmetry in here, again, has to go through the vertex. So that would put our axis of symmetry at x equals 3. That's where it crosses the x-axis. And then for our third graph, again, if you want to pause here, try it on your own, then you can unpause. So on this one, our axis of symmetry is at x equals -2. My line's a little off on that one. Trying to get used to this new tool. So the next thing we're going to look for on our quadratic functions is the y-intercept. The y-intercept, just like when we did linear functions, is going to be the point where the value of x is 0, or on a graph, it's going to be where the function crosses the y-axis. So for our first graph, here is where our graph crosses the y-axis. So we would say that this one has a y-intercept of 0, -3. It would be written as an ordered pair because it is when x is 0. For our second quadratic, here is where our y-intercept would be, and that would be at the point 0, 7. And again, for the third one, if you want to pause, try it on your own, you can. This one would have a y-intercept at this value of 0, -3. So that's where the function is at when x is 0. Now we're going to look for x-intercepts. X-intercepts are going to be a little bit different because the function can have 1, 2, or no intercepts at all. So what we would want to look for is values where the function itself is at 0. So that would be where y is at 0. On a graph, this would be where it crosses the x-axis. Since it is the value when the whole function is at 0, when y is at 0, then sometimes these are called the zeros of the function instead of being called the x-intercepts. So if you ever hear them asking for a 0, they're talking about the x-intercept. Okay, so for our first graph here, we have 2 places where the parabola crosses the x-axis. So this particular function has 2 zeros. So we have one that's going to be at -2, 0, and another that's going to be at 6, 0. So that one has 2. This one in the middle doesn't have any zeros. You can see here that the graph stops above the x-axis and it opens upward, so it never actually crosses. So this one has no zeros. So again, if you want to pause, try the third one. For the third one here, we also will cross twice. So our zeros are going to be at -3, 0 and -1, 0. Now I realized that I did not show you guys one that has only 1 0, so I'm going to go back to this middle graph and see if I can kind of sketch that for you. If you had a quadratic function that looked like this, where the vertex itself was on the axis, then this is a situation where you would only have 1 0. So this one would have a 0 at 6, 0. This is one of those special circumstances where you have a binomial squared to create that quadratic parabola. And that brings us to domain and range. Now, domain and range are really going to be based on that minimum maximum that we talked about at the beginning. Now, domain is all the values of x that you could input into the function. So as long as there are no restrictions on the function itself or on the graph, then domain will be all real numbers. So what that means is that for x, you could put in any value that you want at all from -infinity to +infinity. So we would say this is all real numbers. If you want to use an inequality statement, then you could say it's from -infinity is less than x, which is less than +infinity. For our range, we do have restrictions on quadratics because the quadratic opens up or opens down. So remember when we talked about this graph having a minimum at -4? That's really important when we talk about domain and range, because range means that it can't be below that value. So the range for this one is going to be such that y has to be greater than or equal to -4 since it's a minimum. So I'm actually going to skip over and do the third one now and come back to the middle in a second. Kind of the same thing. This graph continues to move downward to the left and the right with x, so we could put any value of x that we want in at all. So we would call that all real numbers, or negative infinity to positive infinity. But the range is going to be all values that are below that maximum line. So we would say the range is where y is less than or equal to 1. Less than because it has to be below that line instead of greater. So if you want to try the middle one, you can. Again, here on domain, all real numbers. And then for range, this one opens upward. It has a minimum value there at the vertex. So this one is going to be y is greater than or equal to 1. Can be equal to because the vertex sits at 1. Now this example is dealing with someone who is diving from a diving platform. So you can see here that the platform starts at, it's 48 feet in the air, and the person dives, they raise up a little bit initially, and then they begin their descent here as they move down. This would be the point where they enter the water. So this one has some restrictions because we're dealing with a real life example. So here, our domain would not be all real numbers. Since x is time, we can't have a negative value of time, then we would say that this function does not start until 0. So we would say 0 is less than or equal to x. Now the function also only goes until they're in the water, or if you want to consider when they hit the bottom of the pool, which that's a little far-fetched because honestly, once they hit the water, they're going to come out of that dive and resurface. But we'll just go ahead and go with what the graph has here, which means that they're going to go all the way to the bottom of the pool before they would then resurface. That would put them at 2.3 seconds. So we would say x is somewhere from 0 to 2.3. Meaning that the total amount of time that they're in that dive is somewhere between 0 and 2.3 seconds. Now for range, we have to go with where they started and how far they descended. So this one's going to be a little more challenging because we don't have the exact values. So what I'm going to say is that the pool is 20 feet deep. So negative 20 is the lowest they can possibly go in this dive. So negative 20 is less than or equal to y. And then the maximum is up here. I think it's about 49, but I'm just going to call it 50. And I'm not going to say equal to because I can see that the line does not go up to 50. I'm just going to put it at less than 50. So that should make sure we are including 49. But this would be an example where a graph does have some restrictions on it instead of like the previous slide where domain can be all real numbers. I just wanted to make sure you saw one of those. So this covers the properties of quadratics, and I hope that you found this helpful.